In this discussion, we will talk about solving trigonometric equations that require using identities. Now, in my first part of solving trigonometric equations, I talked about how do we solve basic trigonometric equation. So this is basically a follow-up from that discussion. Before we talk about using identities in solving trigonometric equation, let's recall the situation where we solved sin x equals a number, or cosine of x equals a number, or tan of x equal to another number situations. Now, if you have sin x is equal to a number, we already said x must be equals to 2k pi plus sine inverse of x, or x could be 2k pi plus pi minus sine inverse of x as the general solutions. Now, if in the case of cosine of x equals to b, we said the solution for x is 2k pi plus or minus cosine inverse of b. In the case of tangent, we talked about solution for the x, so x equals k pi plus tan inverse of c. So we are not going to go over the derivation of this. If you need to know how it was derived, please refer back to my discussion about solving basic trigonometric equation. In all three cases, k should be understood as an integer. Now, we will talk about how do we use basic identities while we go along with examples, instead of addressing identities first and talk about solving equations. When we solve equations, we'll introduce the identities that are relevant to solving those kind of equations and why we chose those identities as such. So first example is, let's say cosine of x equals cotangent of x. And I want to delimit my discussion to x to be between 0 and 2 pi. Of course, if you need general solution, we can always use our previous ideas. Now, it's always better to relate any of those trigonometric equations in terms of sine, cosine, or tangent, because we know how to use or we know how to solve those equations involving sine, cosine, and tangents. So if I talk about this equation, we can easily think cotangent of x could be understood as sine of x over, cotangent of x could be understood as cosine of x over sine of x. Now, if I move cosine of x over sine of x to the left side, I will have cosine of x minus cosine of x divided by sine of x equals 0, and I should be able to factor out cosine of x, and I will have in the parentheses 1 minus 1 over sine x equals 0. Now from here I could say either cosine of x equals 0 or 1 minus 1 over sine of x equals 0. So this equation will give a value for the x, and we can use our general solution, or since we are looking for a solution within 0 and 2 pi, I could write x could be equals to either pi over 2 or 3 pi over 2. In the case of 1 minus 1 over sine x equal to 0, we could write 1 over sine of x equals 1, and if I consider sine of x is not 0, then we will multiply sine x both sides and have 1 equal sine of x So what that means is x equals pi over 2. So these are the solutions to that equation. In case we needed the general solution, then if we relax x to be any number from negative infinity to positive infinity, in that case x should maybe equal to 2k pi plus or minus pi over 2, and in this situation x equals 2k pi plus pi over 2. By the way, since this solution included in this, so we could even write the solution as x equal 2k pi plus or minus pi over 2. Now let's look at our second example, where we say 3 times cosine squared of x plus sine x equals 1. Once again, I want to limit my x to be a number between 0 to 2 pi. As I said before, I could easily be writing general solutions if I need to. Now, once again, as I said, it is easy to work with sine and cosine here. However, we have two trig ratios, which are cosine and sine. So it is reasonable to consider changing one of them, either sine to a cosine or cosine to sine. And if you look at cosine square of x, and we do know a relationship or an identity, it says sine square of x plus cosine square of x equal 1. This is a very much used identity, and from here we could be able to solve for cosine square of x, which is 1 minus sine square of x, and we could replace cosine square of x with 1 minus sine square of x. Now our equation will become then 3 times 1 minus sine square of x plus sine x equals 1. Now if I algebraically work this one out, I will end up having 3 times sine square of x minus sine of x minus 2 equals 0. Now if I use the idea of factoring, I will have 3 sine x plus 2 times sine of x minus 1 equals 0, and from here of course I could write sine of x is either negative 2/3 or sine of x is 1. Now this will give us two solutions between 0 and 2 pi. One of them is x equal sine inverse of negative 2/3 which is of course going to be a negative answer, so we had to subtract this from pi. So the first solution is basically x equal pi minus sine inverse of negative 2/3, and the other solution is x equals pi plus sine inverse of negative 2/3. It's supposed to be x equal 2 pi plus sine inverse of negative 2/3. So other one, of course, x supposed to be equals to pi over 2. Now let's look at our third example, where secant square of x equals 2 times tangent of x plus 4. Again, I want the limit from 0 through 2 pi again. Now once again, we have two trig ratios involved in this equation. One is secant squared, other one is tan x. So there is a possibility to change it to one trig ratio or function of another same trig ratio, and we will know we have another identity connecting secant squared and tangent squared. We know secant squared of x equals 1 plus tangent squared of x, and if we substitute 1 plus tangent squared of x in the place of secant squared of x, I will have 1 plus tangent square of x equals 2 tangent of x plus 4. So this will make the quadratic equation in tan of x. So we have tan square of x minus 2 tan x minus 3 equals 0, and this can easily be factored out as tan x minus 3 times tan x plus 1 equals 0. So obviously tan x is 3 or tan x is negative 1. So this will give us a solution x equals 5 plus tan inverse of 3, or x equals tan inverse of 3, and obviously tan of x equals negative 1 will give x equals tan inverse of negative 1, which is in fact negative pi over 4. However, our solution is supposed to be between 0 and 2 pi, so the first solution is x is either 5 pi over 4 or 7 pi over 4. Now let's look at our fourth example. Here we have cosecant square of x minus 2 cotangent x equals 0. Once again, we will limit our x to be between 0 and 2 pi. So here once more we will like to turn both trig ratios, cosecant and cotangent, to a single trig ratio. So it is easy to write cosecant squared in terms of cotangent squared using this identity. Cosecant square of x equal 1 plus cotangent square of x. So if I substitute 1 plus cotangent square of x in the place of cosecant square of x, I will have 1 plus cotangent square of x minus 2 cotangent of x equals 0. So it will become cotangent square of x minus 2 cotangent of x plus 1 equals 0. This is basically cotangent x minus 1 equal to the second power equals 0. So what that means is cotangent of x supposed to be 1. So now here again, since I like to use either sine or cosine or tangent, it is reasonable to change cotangent to a tangent. So if we use the identity cotangent of x equals 1 over tangent of x, so we will have 1 over tangent of x is 1. So that will in turn, if you multiply both sides by tangent of x, we will have tangent of x equals 1. So from here, using our idea, we could use x equals either pi over 4 or x equals pi plus pi over 4, which is obviously 5 pi over 4. Now let's look at our fifth example. By the way, all of these examples are somehow introducing the identities that we normally use during solving equations, solving trigonometric equations. Now this time we have sine of 2x equals 2 times sine square of x. Once again, I want to delimit my x to be a number between 0 and 2 pi. So here again we will use the identity for sine of 2x. So sine of 2x equals 2 sine x cosine of x. So if I replace sine of 2x with 2 sine x cosine x, I will have 2 sine x cosine of x equals 2 sine square of x. Now if I move all those variables to one side of the equal sign, so I will have 2 sine x cosine of x minus 2 sine square of x equals 0. So if I take a common factor, which is 2 sine x, and I will have cosine of x minus sine of x equals 0. So from here we could write either sine of x is 0 or cosine of x minus sine x equals 0. Now if I solve for cosine of x, and it will become cosine of x equals sine of x. So if I divide both sides by cosine of x, and assuming cosine of x is not 0, we will have tangent of x equals 1. And of course sine x equals 0 will give us x equals either 0 or pi or even 2 pi. In this case tan x is 1, so that means x is either pi over 4 or 5 pi over 4. Now let's look at another situation where we have to use cosine of 2x. So let's write this equation. Cosine of 2x equal cos x minus 1. Once again, cosine of 2x has 2 or 3 identities. So cosine of 2x could be written as 1 minus 2 sine square of x, or even you can write this as cosine square of x minus sine square of x, or 2 cosine square of x minus 1. Now since I do have cosine of x in that equation, it is reasonable to use the third one, which is cosine of 2x equal to cosine square of x minus 1. So if I replace cosine of 2x with 2 cosine square of x minus 1 equal cosine of x minus 1, obviously we will have a situation it says 2 cosine square of x minus cosine of x equals 0. So what that means is either cosine of x is 0 or 2 cosine of x minus 1 equals 0. So in other words, cosine of x is 0 means x is either pi over 2 or 3 pi over 2. In this situation, when we write 2 cosine of x minus 1 is 0, so that means cosine of x is 1/2. So x is either pi over 3 or 5 pi over 3. So these are the solutions to the given equation. Let's look at another example again. We call it example 7. Cosine of 2x equals sine of x. Now in this particular case, we need to change the cosine of 2x in terms of the sine. So we could use the idea that cosine of 2x equal 1 minus sine of 2x. So if I use that idea, cosine of 2x is same as 1 minus 2 sine square of x equals sine of x. So if I manipulate algebraically, I will have 2 sine square of x plus sine x minus 1 equals 0, and we can easily factor this one out as 2 sine x minus 1 times sine x plus 1 equals 0. So that will give us 2 sine x minus 1 is 0, or sine x plus 1 is 0. So sine of x is either 1/2 or sine of x is -1. So from here we will get x is either pi over 6 or 5 pi over 6. From here we could say x equals 3 pi over 2. Now let's look at another example. We call it example 8. Here we have 3 minus 3 cosine of 2x minus 2 sine squared of 2x equals 0. Now here all of the angles are in terms of 2x, so the only thing that we had to figure out is how do I change sine to cosine or cosine to sine. Only way we could change that is using the idea that sine square of 2x plus cosine square of 2x equals 1. So that will solve, if we solve for sine square of 2x, we'll have sine square of 2x equal 1 minus cosine square of 2x. So if I substitute that into the given equation for sine of 2x, I will have 3 minus 3 cosine of 2x minus 2 times 1 minus cosine square of 2x equals 0. So if I algebraically manipulate this, I will have 2 cosine square of 2x minus 3 cosine of 2x plus 1 equals 0. So this could easily be factored out as 2 cosine of 2x minus 1 times cosine of 2x minus 1 equals 0. So what that means is 2 cosine of 2x minus 1 equals 0, or cosine of 2x minus 1 is 0. So this will make cosine of 2x to be 1/2, or cosine of 2x is 1. Now if I want general solution, it will be 2x equals 2k pi plus or minus cosine inverse of 1/2, so which is same as 2k pi plus or minus pi over 3. So if I need to solve for x, I have to divide everything by 2, so x equals k pi plus or minus pi over 6. So that's the solution coming out of the first set of factors. And the second set of factors will give cosine of 2x is 1. What that means is 2x is same as 2k pi plus or minus cos inverse of 1, which obviously is 0. So we have 2x equal to k pi, so x equals k pi. Let's look at another example. Although it is a little unrelated, however, it is in relation to solving trig ratios anyway. Let's say tan of 2x minus pi over 3 equals 1. And how do we solve this equation for x? So again, if you use general solution, 2x minus pi over 3 is supposed to be equals to k pi plus tan inverse of 1, which is in fact is k pi plus pi over 4, which is 45 degrees. Now if I solve for 2x from here, 2x will be same as k pi plus pi over 4 plus pi over 3, which is same as k pi plus 7 pi over, or 7 over 12 pi, in other words, which is equal to 2x. So if I need x, I need to divide both sides by 2. So I have k pi over 2 plus or minus 7 pi over 24. So this example will illustrate how do we use the general solution to find x, or the variable, even if you have x as a x within a function.